Hey guys, a while ago we said that calculus is the math of change and that all derivatives are basically slopes, ways to find slope of any formula, any equation. And the whole goal is to put these things together with real world problems. And that is what we're going to do with this section is we're going to start to work with real world problems and how that can work together with our new knowledge of calculus. So there's a basic procedure for these related rate problems. Now they're called related rate problems because the slope is also characterized as the rate of change. So since calculus is about change and slope are derivatives and all those things work together, these are called related rate problems because they deal with the slope or the changing rate of the equations that we're going to come up with. So, now since these are all word problems, the first thing you're going to do is read the thing, always. With what you already know about word problems and how to make them a bit easier on yourself, you can go through them that way with that in mind. And any hints and helpful things that will make it easier on yourself are always nice. You're going to end up writing one or more equations, and then we're going to differentiate with respect to time. Now that's a key thing for any type of word problem or real world problem is most of the time, no pun intended, you are differentiating with respect to time. So you're going to have multiple slopes all with respect to time as you go through. So this is one of those things where our notation is really going to help us out if we use the ddt or ddy or ddx or whatever they're asking us. If we use that type of notation, it will definitely help us out because of all the variables that we're going to be dealing with, and they're all going to be changing at the same time. Okay, so let's have this first example here. The legs of an isosceles right triangle increase in length at a rate of 2 meters per second. What is the rate? At what rate is the area of the triangle changing when the legs are 4 meters long? At what rate is the length of the hypotenuse changing? Okay, so the very first thing that occurs to me is, well, do we remember what an isosceles right triangle is? An isosceles triangle is a triangle that has two sides that are exactly the same length. A right triangle has a right angle. So an isosceles right triangle must have, or must be, something like this, where we have the right angle and then we'll have the two legs that are the same length, and then the hypotenuse will be different. This is significant. Anytime they give you shapes or such things like this and you don't know what it means, look it up. That's what Google's for. Or Siri or Alexa or whatever is your favorite, you still have to be able to work with whatever they're talking about or whatever they're telling you to. So make sure that you understand that part. So isosceles right triangle. It'll have a right angle, and by definition of it being isosceles, the two legs will be the exact same length, and we'll just use x for convenience. So it says an increase in length at a rate of 2 meters per second. So per second means we are doing with respect to time. That's good. And this thing, it says the legs will increase in length at a rate of 2 meters per second. So rates, any rates, are slope. Any rate is a slope. So this means that the legs, well, if we call the legs x, then as the legs change, dx dt, they are changing at a rate of 2 meters per second. So remember, all derivatives, all slope is a rate. So this first sentence here gave us a lot of information. The isosceles right triangle gave us the shape. Our knowledge of what an isosceles right triangle is gave us the length of those legs. And then it says that the rate changes. So that gave us the slope. Okay, and that's just the first sentence. So let's take a look at the next sentence. At what rate, okay, so they're finally asking us a question. At what rate is the area of the triangle changing when the legs are 4 meters long? So, key word there is area. What do we know about the area of a right triangle? Well, we know the formula of it, don't we? So the area of a triangle is 1/2 length times width. Ta-da! There you go. So now we're going to adapt it to our triangle in particular. So we still going to have the 1/2 part. That's not going to change. So our area, 1/2. Well, this length times width part is based on the base and height of the triangle, not the hypotenuse. So our length and width are actually the same thing here for our isosceles triangle, and that's x. So x times x is x squared. If you don't remember a formula, look it up. That's why we have them, and Google is awesome. So now that we have this lovely formula here, we can differentiate both sides with respect to t. So I'm going to take d dt of each side. So this will give me the area with respect to time, and, well, formula 1/2 x, 1/2 2x dx dt. 1/2 times 2 disappears, so I have this lovely formula. Lovely. I think I can answer our first question then. So at what rate is the area of the triangle changing? That means that I am talking about dA dt. When the legs are 4 meters long. So my dx dt doesn't change. That's what they told me, right? So dx dt is 2 meters per second. And then our legs are 4 meters long, so that would be our x. So this would be 4 times 2 is 8, and I've got meters squared, because there's 2 of them and I'm multiplying, so meters squared per second would be our dA dt. For the next question, we did that part. For the next question, it says, at what rate is the length of the hypotenuse changing? So we're not talking about area anymore. We don't need that area formula. What we're going to need is the formula for side length of a right triangle. So that is the Pythagorean theorem, otherwise known as a squared plus b squared equals c squared, where c is always the hypotenuse. We adapt it to our specific problem. So we have the two lengths are x, so x squared plus x squared equals our hypotenuse squared. So I'll just put h for the hypotenuse, that's easy enough. So that gives us 2x squared equals h squared for our formula. Wonderful. So now we need to take the derivative with respect to time. So d dt of each side. Okay, so 2 times 2x dx dt and 2h dh dt. So that gives us 4x times 2 meters per second, 2h dh dt, and the rate that the length of the hypotenuse is changing, that means that I'm trying to solve for dh dt. Okay. We can easily solve the equation that we have for dh dt. Very simple. So that'd be 8x meters per second over 2h. The problem is that a rate doesn't have variables. We need a number. So how are we going to figure out what that is if they don't tell us what x and h are? Well, that means that we're talking about a very, very generic form. So if they don't tell us explicitly, we get to do this ourselves. So let's go back to the basics. If our isosceles right triangle has a leg of x, then by the formula of the Pythagorean theorem, that means that the hypotenuse will be the square root of 2x squared in length, or x square root of 2 in length. So we can actually substitute our h for that in mind. Which would also be in meters, by the way. Okay, well, anything over itself cancels. So the x's would go away. So we would have 4 over the square root of 2 meters per second. And we don't like square roots in denominators, so we need to rationalize the denominator. So that would give us multiply by square root of 2 top and bottom. So that'd be 4 square root of 2 over 2 meters per second. And that'd give us 2 square root of 2 meters per second for our dh dt. So first you have to work with what you know, what they give you, what they're asking you for, bit of substitution, taking the derivative with respect to time, substitute anything else we need, and then work it out. So one thing at a time as we go along. So this was pretty generic, not more hypothetical than real world. So let's do an actual real world one. We have an oil rig springs a leak in dead calm seas, meaning that there's nothing affecting the surface of the water, not wind, not the moon, nothing. The oil then would spread in a circular path around the rig. If the radius of the oil increases at a rate of 30 meters per hour, how fast is the area increasing when the patch has a radius of 100 meters? Now, if they don't give you a picture like they did on the last one, we drew it ourselves. This one, they gave it to us, which is always nice of them. So, what do we know about circles? Are we talking about area? Are we talking about surface area? Are we talking, what are we talking about? So oil and water don't mix. So we are not talking about volume, we're talking about surface area. So the area of a circle is pi r squared, as we know. So we need to take the derivative with respect to t. So d dt of both sides. Okay, so that gives us the area with respect to t and 2 pi r dr dt. Okay, so now what about the numbers that they give us? So this says the radius increases at a rate of 30 meters per hour. So radius 30 meters per hour, so that would be dr dt. And then it gives us the radius of 100 meters. So they have given us all the information we need to finish. So how fast is the area changing? Well, that's dA dt that we're looking for. So then 2 pi times the radius. Well, the radius they told me is 100 meters. And then the rate of 30 meters per hour for dr dt. Multiply as you wish. So we have be 6,000 pi, and then that'd be meters squared per hour. So be careful. Sometimes you have to work with what you know. Sometimes they give it to you, and it depends on the problem. The easiest way that I know of is to just go line by line, exactly as we've done in the last two questions. All right, let's do another one. So a regulation rectangular swimming pool, 10 feet wide, 20 feet long, and a uniform depth is being filled with water. At what rate is the volume of water increasing if the water level is rising by a quarter foot per minute? And what rate is the water level rising if the pool is filled at a rate of 10 cubic feet per minute? Okay, so this time they didn't give us a picture, so let's draw it ourselves. If we have a rectangular swimming pool, and a lot of the times they will do this, they'll simplify the problem as much as they can because the interesting shapes come later, and pardon my bad drawing. So we have 10 feet from here to here. We got 20 feet from there to there, and a uniform depth. So, yeah, bad drawing, which we don't know, but we'll just call it D. Okay, so then they say, at what rate is the volume of water increasing? Well, volume, what do we know about volume of rectangular things? Well, that would be length times width times depth of all rectangular things. Okay, so based on our formula and our shape, we can say that the length is 20, the width is 10, so that's 200 times the depth. And now we can take the derivative with respect to t. So dv dt would give us 200 dd dt, with, as long as you remember, that's the derivative with respect to depth. Yeah, I don't like that. Well, we'll use capitals there. If you can't read your own handwriting, you're going to get in trouble. So be careful. All right, so now I think we can take a peek. So at what rate is the volume of water increasing? So I'm looking for dv dt there. If the water level is rising at a quarter foot per minute. So that's the depth. Water level would be depth. So 200 times 0.25 feet per minute would give us the change in volume. And that would be 50. Now I want to say feet per minute, but that's because I accidentally made a mistake. It's not feet per minute, it is cubic feet per minute. Now I know this because volume always comes in cubes. But so where did my extra 2 feet come from? Well, they came from the 200. Length is in feet and width is in feet, so this 200 is 200 feet squared. In essence, that 200 is actually the area. So be careful. Now that's the first one. In our first example, we had area and then we had length. I needed to change equations at that point. Do I need to do that here? Well, no. At what rate is the water level rising? Well, water level is depth, so I'm still dealing with volume, which means I can still use the same equation. If the pool is filled at a rate of 10 cubic feet per minute, that's a really big hint. 10 cubic feet per minute, that's a volume. Anything that has a cube unit is a volume. So if my dv dt is 10 cubic feet per minute, 200 feet squared, and I'm looking for the change in depth of time. So divide by 200 on each side, and that'll also divide out your feet as well by 2 of them, which will give you feet per minute, which is perfectly fine and awesome because that would be depth. So 10 divided by 200 is 1/20 feet per minute. So use what you know and go from there. Okay, here's another one. 2 small planes approach an airport, one flying due west at 120 miles per hour, the other flying due north at 150 miles per hour. Assuming they fly at the same constant elevation, how fast is the distance between the planes changing when the westbound plane is 180 miles from the airport and the northbound plane is 220 miles from the airport? So they gave us a nice picture with this. Notice that it says y of t, z of t, x of t. Well, that's to remind you that you are working it with respect to time. So, I personally prefer the d dt, but that's just me. What's significant is picking what you like and what you understand the best and doing that all the time. Habits are a good thing. Okay, so if we're talking about distance, and that's the same thing as a triangle, then we're talking about the side length of a triangle. So we're talking about the Pythagorean theorem again. So a squared plus b squared equals c squared. So in our case, that would be, well, x squared plus y squared equals z squared, or x of t squared, y of t squared, etc. So now we would take the derivative with respect to t everywhere. Easy enough. So 2x dx dt plus 2y dy dt equals 2z dz dt. Okay. Now they gave us a lot of numbers here. We just have to figure out which one's which. So, two planes, one flying due west, north, south, east, west. So this would be the westbound plane. No, it's not. This one's the westbound plane. It is going west, so westbound. There you go. And then the northbound plane would be the one going north. My bad. You can't answer a question unless you know what it asks and you can translate. Okay, so now we can actually work with it. So, one flying due west, so this would be our westbound plane. That's 20 miles per hour. That's its rate. And the north is 150, so that would be its rate. 180 would be the westbound plane's x. And then 225 would be the northbound plane's y. So with that in mind, we can work with our formula. Let's substitute in what we know. So if the west one is x, so that gives us 180 miles, and it's 120 miles per hour, plus 2 times our y here, our northbound, so it is 225 miles, and 150 miles per hour equals the rest of it. Okay, let's actually run that through with our calculator since I ran out of room on the page. And I also went ahead and divided by the 2 in front of the z. Now, this is all fine. It's wonderful. Except we can only figure out one thing at a time. And what are we trying to find? Well, we're trying to find how fast is the distance between the planes changing. Okay, so we're actually looking for dz dt, which means we need to know z. Well, fortunately for us, we do, or we can find it. Since we know that x is the 180 and the y is 225, we can use our Pythagorean theorem to figure out what z is. So 180 squared plus 225 squared, and then take the square root of that. So that gives us a lovely 288. So our dz dt so we get, ooh, that's interesting. So we get a lovely 192 miles per hour. Now this is slightly strange. Why is it strange? Well, we are getting closer to the airport, which means these two planes are getting closer together. So a positive slope, a positive rate of change, would indicate that it is increasing. So that would be the distance between them is increasing, but that doesn't make sense since they're getting closer together. So this should be a negative 192 miles per hour. And the reason is mathematically why it's not here is because this distance is decreasing. So this lovely 120 and 150 that we used is actually a negative because they are getting closer to the airport. So they are decreasing their rate, which means they're getting closer and closer, and thus it is a negative. I did not take that into account the first time through, so my 55,000 is a positive when it actually should be a negative. So be careful there. I didn't even catch that mistake until the final answer. Sometimes that happens. Negatives are easy to miss, so be careful. Anytime you're looking at decreasing things, your rate is going to be a negative.